Great. Good morning. My name is Anthony Torza. I work at Cisco in the Hardware Systems Division. I'm here with Wei-Jen and Jane to talk about 51.2T system design. So one of the things that we should start out with when designing a switching system for any bandwidth is, the heartbeat, the core of the system is really the switch ASIC that's in the center of it all. And this is kind of a recap of what that progress has been over time, because it forms the foundation for what we're building when we build a 51.2T system. So back in the good old days of 2010 and 10 gig SerDes being exotic, we had a 64 radix, 10 gig SerDes. And then as we moved forward in time, both the radix of the switch chip and also the speed of the SerDes sort of tick-tocked as they increased. So you can see as we scale up to 51.2, we have gone from 10 gig and a 64 radix to 100 gig and a 512 radix. So obviously there's a lot of complications behind this scaling from a systems perspective, and how you manage those as a system architect and a designer is the key behind proper system design. And so we're going to talk about some of those trade-offs as we as a community look forward to 51.2T switch design as those semiconductors start coming out. And then perhaps there will be questions, so I included beyond that, as we scale to the next generation after at 102.4 tera, this is where things get even more interesting. That's not the topic of this talk, but I'm sure there will be some questions because there's been a lot of buzz about that. But the other thing to note as we scale the switch radix and we scale the speed of the interface is obviously what optics plug into it. So you can see at the bottom we started with QSFP+, and then we scaled up to QSFP 28, and then to QSFP DD, so we increased the radix of the optic as well as the switch. We went from 4 lanes to 8 lanes. And then we've scaled forward to the QSFP DD 800, and there's also other alternatives if you wish in the OSFP camp. There's a 400 gig OSFP, which is not widely adopted by most customers, but as we look forward to 100 gig per lane, there is an OSFP 800 standard as well. So the 51.2T design, around that ASIC, then let's put some boundary conditions on that as we discuss implementation trade-offs. And so we've already walked you through the roadmap from 2010 to an ASIC where we're postulating a 512 by 106.25 gig SerDes ASIC, and then that naturally maps at 100 gig per lane to 64 optics. In this case, QSFP DD 800. Again, OSFP 800 is a perfectly fine choice as well. That defines your faceplate. So if you want maximum density with 64 modules, then 2RU is the minimum size for the faceplate. So that defines one of the boundary conditions that we're working on. Then obviously a motherboard, a CPU for control plane, front and rear panel ports for control traffic and I/O and timing and control and things like that. And then space for redundant AC, DC PSUs, likely swappable because a lot of different deployment scenarios require either high voltage AC or DC. And then of course, increasingly importantly, we need fans to cool all of this as we scale up. The Dennard scaling has not been serving us well, as many papers have come out over the years as, despite marketing claims, we're still rapidly ratcheting up on power. Note that the assumption of the 100 gig per lane to the 800 gig optics also has another choice, is we as an industry have been discussing a 1.6T pluggable form factor, which is actually a talk that I'm covering for later today. So if you can't get enough of me now, you can go see my talk later about 1.6T, but there are options in the XD form factor at 100 gig per lane, and then as we look forward to the QSFP DD 1600, but those are faster rates. So let's talk about the system design. So as we delve into how we build things within the box, as an engineer, we generally like to be done on time. Our bosses generally tend to pay us more if that happens, and it also needs to work. And so the primary trade-offs that we are making as engineers and system designers is, what do we need to invent to achieve the implementation that meets the success criteria we defined on the previous slide with the minimum risk possible. So the rest of this presentation is really delving into what this slide summarizes, which is on 4 key metrics of how you deliver power to the ASIC, how you cool the ASIC, how you cool the optics, and how you interconnect everything together. On the high-speed side, there are a number of different choices with different risk profiles. And as a system architect, you typically will trade some of these for the other. You don't always get to be in the low-risk bucket for all of the things. So there's a number of trade-offs to make. But let's walk through them briefly, and then we'll dive deeper on the following slides. So on the power delivery slide, as I mentioned, the ASIC power has been going up, and for thermal reasons, we've been trying to keep that as low as possible. What that has meant is we've been trying to drive the gate voltage down on the ASICs, which means actually that the current has been rising a little bit faster than the power because the voltage has been dropping to combat that. So we are now facing, some of the rules that we were defined in the IPC specs in 2008, 2009 about current density within the circuit boards. You have to manage that very carefully to make sure you have the reliability that you need. It's the only thing worse than being late is shipping on time and then having a bunch of RMAs come back from a customer. That's really bad. So you have to meet those requirements. So there's different trade-offs, and there have been a number of industry papers about integrating the voltage regulator, so stepping down from the high voltage to the low voltage on the ASIC package. And then there's the more traditional approach, and we'll compare and contrast both of those. On the ASIC cooling side, traditionally we've had lidded ASICs and air cooling. Looking forward, there's been a number of work, primarily started in the graphics industry, but is now propagated to other industry segments within semiconductors about removing the lid from the ASIC, and we'll discuss the trade-offs there, but sticking with air cooling. And then as you've seen, probably if you've been to the Meta display booth and a few other booths here, there are a lot of customers starting to experiment with in-rack liquid cooling. And so the question is that necessary right now? And I, as an engineer, put it at high risk because it's not a qualified technology yet, but there are a lot of good works going on to get it to that. Then on the optics side, the optics are also scaling up, and actually they are suffering some of the similar effects that we are on the switch, that the power is not, the density is increasing, but the power is not keeping the same. So there are a couple trade-offs in terms of whether you do the heatsink design as part of the system, which is what you do for QSFP-DD, or if you integrate that into the module, which is the OSFP approach. There are also ways to augment that, particularly using thermal interface materials on the optics cages, and heat pipes and other more exotic ways of pulling the heat away from the optics cages, which we have already started to use on the ASIC to pull heat away and distribute it better. And then on the right, again, is liquid cooling. And then on the high-speed side, we compare and contrast from a risk perspective the circuit board materials, and we've been very impressed with the progress so far, but there is some tailing off on the scaling as we go to faster speeds of the SerDes. The loss per inch of the circuit board material has not been keeping up with what I would call our expectations. They would call them unreasonable. We would call them completely reasonable. But, oops. Look at that. Okay. That gives you an idea of what's going on today. Okay. I don't think this is on. Oh, well. I have enough battery, so I should be okay as long as I pay attention to the sleep. Speaking of power. And then there are other choices as well, right? There's been a lot of press about using flyover copper cables to bypass a large of the long traces on the circuit board, and you can actually see those in a number of systems demonstrations in these trade shows like this. And then there's the perennial discussion about co-packaging the optics, which is extremely sexy and we'd all love to work on, but the real question is it necessary for this node? And it is higher risk because there's enormous system complexity trade-offs required for that. So let's go through that. So on the power delivery side, we have VRMs that are around the perimeter of the ASIC. So one way that you can combat the current density issue that we discussed earlier is instead of putting all the voltage regulators on one side where all the current needs to enter the ASIC pin field from one side, you can place them around the perimeter of the ASIC die. Now, of course, there are trade-offs here on the high-speed side, and we'll talk about that when we get to the high-speed side. But from a current density perspective, we have this as an option. Typically, these are multi-phase in order to keep with a very low ripple so that we can get the gate voltage as low as possible. We really need to design for the lowest of the voltages. So if we can control the ripple better, we can bring that voltage down and we get a V squared effect, right? Because power is V squared CF. So if we can get the voltage down a little bit, that can help. So putting it around the perimeter allows us actually to use more phases to control that ripple better. And so this allows the maximum current entry on all sides. And it also allows a better response for dealing with transients. So typically in switch silicon, we have SerDes running most of the time, so those supplies are relatively consistent in their current profile. But on the digital side, if you were to have a spike in traffic, for instance, you may see a transient response on the digital rails in the core. So that's important as well as to design with enough capacitance to handle that. On the integration of VRM side, there's been a number of papers. Probably the most famous is Intel's Fiverr paper a number of years ago about integrating the voltage regulator on to the package. Now, this is a very interesting technology. It has a lot of trade-offs, but it has two cons which really play against it. The first is you need a bigger substrate, and those of us who are making ASICs these days know that the hardest thing in the world to get right now is substrate capacity. So convincing a substrate vendor to build a lower yield, larger substrate will mean that your costs go up, and then your customers will not be happy about that. The other side is, on the thermal side, we're also compating a large thermal density hotspots within the box and moving the voltage regulators onto the package, and typically there's about 10% loss in those regulators, just increase the thermal density of what's on your package by 10%. So this is an interesting technology, but this goes in the only if it's necessary bucket for us. For us in our work on 50 terabit systems, this technology is not necessary. And you'll see, while there have been some discussions on the CPU side, that is not really needed in outside of the CPU realm. Okay, so let's talk about ASIC cooling. So as we've, in that chart where I showed you how bandwidth and radix and SerDes speed and optics density scaled over time, one of the things that sits behind that chart is how is power scaling. So typically, the power will rise with the scaling of, with the bandwidth, but then you're combating it with more advanced process geometries. So if you are, say for example on TSMC, they'll say our next generation process node is 30% less power on the digital rails, and then they won't really tell you as much about what happens to the analog voltages and things like that. But in general, if we look at this in the system context from 2010 to the 51 tera land, you can see here on the chart how power is scaling. So first of all, on the ASIC core power side, because it's a digital rail and the concentration of our semiconductor suppliers has been on the digital power rails, we've gone up almost 50 times in bandwidth, but we have 8x increase in ASIC core power. So that one's actually reasonably well controlled. What is not as controlled is what's happening on the analog side. The SerDes power, as we increase the radix and the speed of the SerDes, has been going up by a factor of about 25. And then the optics power has also been rising because they have the same SerDes on their host interface, but they also have SerDes on the media interface, and they have things like lasers, which are based on more mechanical effects than semiconductor-related effects. So those do not scale as readily with process geometry. And then, of course, we need to cool everything, so fan power has risen as well as we have tried to combat this. So the goals of a good design is to keep the semiconductor junction temperature below the maximum operating temperature, which is typically on the order of 100 degrees, depending on geometry. It can be 105, 110. It depends also on your static timing and how aggressively you close that and what your usage is of transistor types. And we maintain, or at least our customers maintain, that while they're very interested in what roadmap is to liquid cooling, the primary design scope for 50 tera remains air cooling, so we need to consider that. So one way that we can improve the efficiency of air cooling against these headwinds is to look at removing the lid from the package. So what I've shown here on the left side of the screen is a conventional lidded package. So in blue is the semiconductor die. It connects to the vapor chamber heatsink where the majority of the heat gets transferred out of the system via heat pipes and other means via actually a fairly complex sandwich. So there is a lid on top of that die. But since that lid is made of copper and the semiconductor die is made of silicon oxide, they behave differently with temperature. So you need to have what's called a thermal interface material between that and the lid. And then again, since the vapor chamber is typically a hollow copper chamber, and the lid is as solid of a copper lid as you can get for other mechanical reasons, you also have different behavior with thermal. So you need another thermal interface material between those two. And there's ways to get that as low as possible, but fundamentally because of the warpage and the thermal expansion and contraction of those systems, you need some sort of some way to smooth over that interface. And so typically those are not as conductive, right? Like you have a piece of copper that is like 300 watts per meter Kelvin. It's great at pushing heat around, but the thermal interface material, because it needs to be semi-liquid, it typically will be some sort of paste with metal particulate in it. And so that'll be more on the order of 3 to 6 watts per meter Kelvin. So that's way less in terms of the efficiency. So one of the innovations that we as an industry have been working on, and credit to the graphics guys for going first on this a few years ago, was to remove the lid and then only have to deal with one thermal interface material between your vapor chamber and the die. So that reduces the thermal resistance to the heat conducting things, and it gets heat out of your system more efficiently. So just to sum up for executive summary reasons, lidded, in our experience, works up to probably pretty well up to 400 watts. There's a lot of small details on the system side that add a little bit of risk, so that's why I put lidless in the medium category, but lidded in the low category. So you'd like to stay in lidded as long as possible, but lidless is helpful at all power levels because, again, the resistance is lower. I think it becomes necessary really above 500 watts, and it does have some headroom. Of course, we have not yet managed as an industry to produce a 1,000-watt ASIC, and I do not encourage that behavior, but the experiments we have done is that we can pull many hundred watts out of it, perhaps up to 1,000 watts with lidless. And then after that, I think, depending on what the heat flux is in watts per square millimeter of die area, that's where you start to evaluate the transition to liquid cooling, which is in the high risk category. So just to sum up to 400 watts lidded, but I think in this generation we're seeing a transition to lidless to help with power consumption. So let's move to the optics cooling portion. As we mentioned earlier, the optics modules, they increase the data rate of the 8-lane interfaces on both the OSFP and QSFP DD form factors from 53.125 gig to 106.25 gig. So that obviously increases the power consumption of that. And because of the tight space defined by the form factor that existed quite some time ago, the module design is a little bit challenging on the inside. So they optimize for signal integrity because of that move to 100 gig, but also they do the best they can on thermal management. So it's our job as system designers to help them get across the finish line on that. Both QSFP DD and 800 and OSFP 800 form factors are available. And I'm going to summarize the pros cons, but I'll let you read them in the slides afterwards. Generally, the QSFP DD form factor puts the onus of thermal design for the optics on the system designer. So you design the cage and the cage heatsink, and you optimize it for your system. So that allows you to design heat sinks that capture all the air that comes in through the faceplate. So it's one of the advantages of allowing the system designer more degrees of freedom. It also allows you the ability to cool more efficiently. On the OSFP 800 side, the heatsink is built into the optics module. So in theory, it is better at cooling, but the size of the heatsink is fixed by the form factor. So you don't have any ability, and since it's not even made by you as a system designer, you're dependent on all your suppliers for that. So you need to design to the least common denominator of that. So as we have risen from 100 gig to 400 gig to 800 gig, the optics power has risen quite a bit. So there are issues with that. The other issue is you also have other things in your system that need to be cooled. And if the heatsink on the optics is very small, which unfortunately it is in OSFP, you need to have a vent to bypass that so that the fans can operate efficiently to cool the NPU behind it. So you're not able to capture all the air that comes in through the faceplate. And then on the high-speed side, as benefiting this as maybe the highest complexity part, there's a lot of small text on here. But the key trade-off here is getting from the ASIC to those 64 modules on the faceplate. As circuit board technology scales, we have a target of getting below 1 dB per inch at temperature, because of course on the thermal side we're trying to manage that, so we're not able to keep this suspended in liquid to keep the circuit board cool. So we have to design for those type of interfaces. There are options with advanced stack-ups and higher layer counts to get all of the ASIC traces to the front panel, but we're increasingly seeing as an industry the use of flyover cables. And this is a new introduction in 50 tera for some or all of the links from the ASIC to the faceplate. This has some trade-offs. The first trade-off on the plus side is, in theory, it allows you to step maybe 1 or 2 steps back from the most advanced circuit board that you could possibly build, which can save some cost, but then you have to pay the cost of the flyovers, and that has to balance in a realistic manner. The other problem is there's a new mechanical interface in your system. So you have a connector that wasn't there before, and any hardware engineer who's dealt with a connector those need to be reviewed with 10 times the scrutiny as any other interface because the reliability is not as good. So let's sum up where we think we are for 51.2T. So this is a reprise of the earlier slide with my opinion on this, but I encourage the discussion after the talk. On the power delivery side, I think we've established that we do not need to move into integrated voltage regulators, which is good, so we can stay in the low risk camp. On the ASIC cooling side, though, because of the power scaling challenges that we're seeing in semiconductor technology, especially on the analog side and SerDes side, and especially as we look forward to 200 gig per lane, we're accepting a little bit more risk to remove the lid from the semiconductor to cool it better. On the optics cooling side, I think we have two great choices in terms of the QSFP-DD and OSFP form factor with the trade-offs we discussed earlier. So there's no need for necessarily liquid cooling those. We think we've proven we can cool up to about 30 watts in either form factor. And then on the high-speed interconnect side, there's really some choice in the matter of either advanced PCB, which can create some cost implications on the circuit board side, or on the PCB plus flyover cable side, where there is some more mechanical complexity and potentially there's some cost trade-offs. It's also still proving out as a technology, so we need to make sure that we have the right scrutiny on those from our suppliers. So from a call to action, I think what we'd like to request of the community is that we cool the optics through better QSFP-DD cage designs, but also improved OSFP heat sinks that are appropriate for the 800 gig power levels, especially as we look at ZR optics, the 80 kilometer and 100 kilometer plus reaches. We need to have an ASIC with the appropriate, or a heat sink with the appropriate volume. As we look forward to 200 gig per lane, I think we have a really tough decisions to make on what the host budget is. You've seen Cisco present. We're presenting that to keep the current architecture, we need 35 dB from bump to bump, from the optic to the ASIC, and that has power implications in terms of power scaling. And then I think we really like to encourage the industry to standardize and multi-source flyover cables, because we will get there at some point in the near future, and we'd like the cable vendors to work together to have a more realistic MSA style way of approaching this rather than the current way of everyone having proprietary connectors. Thank you. So I think I have time for maybe one question. Yeah, there's some microphones there if you'd like.
Good morning.
Hey, Ali, how are you?
The question I have is for a past 200 terabit. What do you think? Is it going to be 1,000 SerDes, or is it going to be a 512 by 200? And if it's going to be based on a 200, where do you think that can be commercially available, with a 200 gig SerDes? Because it seemed to be that in terms of timing, you would have to take some time off.
So sorry, make sure I understand your question. You're talking about past 51T to the next node after that. I think we're trying to figure that out as an industry, right? Like we haven't gotten, as you know more than me probably, on the 802.3df, there is still an unsolved host budget, but I think we're vectoring towards PAM4 as the system side. I would say that if you look at where the SerDes IP vendors and retimer vendors are headed, there is, I think motion on 200 gig that the technology will be there. Right. But the decision, it needs to still be made about what that looks like. But it's a good question. Yeah.
This pass of every 2 years doubling the bandwidth, it just doesn't seem to be it's going to happen, at least with 200G in my opinion.
I would say there are paths to get there. The question is, do you want to keep it maximally low cost? But I have discovered through my friends' children that there is an insatiable need for more bandwidth, so someone's going to want to figure it out. So we have no choice, sorry. Sorry. Can you?
I think, yeah, we don't have time for now.
Oh, okay. I'm happy to hang out and talk to folks afterwards. Okay. Thank you. Appreciate it. Yeah.